Assalamu alaikum wa rahmatullahi wa barakatuh. So today is our lecture number 22. In this lecture we will start with the topic of variance and standard deviation. So far we have seen the discrete random variables, and one of the important property of that is the mean, which we call it as the expected value of the random variable. So this will give me the central tendency of the random variable. Now sometimes the mean, or we just call it as the mu x, is not the estimated value is not gives us the exact picture. So we have to see the spread of the we have to look at the spread of the data. So that spread actually gives me somehow a good picture that how this mean is related to the data, whether if some of the marks is some of the data points which we are looking for, if they are closer to mean, what does it mean, or if they are further from the mean, what it means. So for that we have to look a bit further, and that further is the spread of the data. Sometimes we can see that how far from the some data is, say, from x mu x minus mu x, so that is gives me the difference of the mean and the random variable. So we have seen that if we have seen in the previous theorem that expected value of this derived random variable y, which is x minus mu x, is always 0. So that only spread by looking at the difference in that numbers is will give us not a very good thing, because will not give us very good picture of the data, because it is always 0. Some of the suggestions are that we take the absolute value of the y, but again sometimes it's not very easy for certain points for the to calculate or find out the absolute value of the y. So there is another way to find the spread, and that is actually as the square of this value, expected value of x minus mu x. So expected value of the square of this difference. So we call this difference as the variance. We call this difference as the variance, and we write it as VAR of x is equal to expected value of x minus mu x whole square. Now there is one important point in if you look at this variance relation. So what we will get is the square of the value of this thing, square of the value of the square of the data. Now just consider if we are talking about the quiz marks of a class. If we are talking about the quiz marks of class, so what this square term will make it square of that marks. So that will give me not a clear picture of what I am looking for the spread. So we introduce another parameter to look at the spread of data. So that is just simply, we call it as the standard deviation. So standard deviation is this sigma x, small sigma x, variance of x square root. Now if you take the square root of this terminology, so it will become a proper units. So that standard deviation will give me the clear picture of the spread of the data. So sometimes we say that if certain data value belongs to mu x minus sigma x or mu x plus sigma x, so we call those values as typical values. We call it that these values lies within the sigma, within the one standard deviation of a expected value. So within one standard deviation of expected value. So sometimes we call these values as the typical values, means most of the values. Sometimes it means observed that most of the, or the 2/3 of observations, 2/3 of observations, 2/3 of observations of a random variable, are within one standard deviation of the expected value. So there is another important aspect of this variance is that is the estimation. So simply estimation is means, in generically we use this terminology to say that even if we don't know what is the exact value of certain things, so we ask about the estimate of something. So estimate is that we make a prior means a prediction of a certain parameter to find out what could be the possible value in the for if we will go for the experimentation. So it is the variance also useful when we guess or predict value of random variable x. So sometimes we call this prediction the prediction. We use the notation x with this small hat on it, x hat, also called a blind estimation of x since we have no observations. So we have no observations, but we have the prediction of random variable x, which is the blind estimate, so that we call it as the x hat. So we would like our prediction error. So obviously when we have the prediction, so it's not the exact value, so we would like the prediction error. We would like the prediction error. So prediction error is x minus x hat. So this is what we have predicted. So that could be the observations. So that we want to be small. So how we can do it? That if we take E error as the expected value of x minus x hat whole square, like this. Now if we can see that it states in the theorem 3.13. So it says that in the absence of observations, the minimum square error this one terminology is called the minimum square error, or MSE in short. So the MSE, minimum square error, estimate of random variable x is x hat, which is equal to expected value of x. Now remember that this estimate is expected value of x in the absence of observations. So we can prove it very easily, because it's just a straightforward method to prove it. So just using this relation, using this terminology, E is equal to x minus x hat. Now if we open this square bracket and apply the linear property of the estimate or expected value, so we can find out it's very easy. Expected value of x square minus 2x hat, expected value of x, plus x hat square. Because x hat is a constant, so the expected value of a constant we have seen is itself constant itself. Now because this is E and we want to minimize this error, so to find the minimum value of a certain relation, we know from our calculus is that we have to take derivative of this function with respect to the parameter we want to reduce or minimize. So dE by dx hat, so this is constant value, so it will be 0 minus, so this 2 will be 2 expected value of x plus 2 x hat, and we have to put this relation equal to 0 to find out the minimum value. So from this relation we can say that x hat is equal to expected value of x. So when the estimate of x, so we can say that when the estimate of x is x hat is equal to expected value of x, the mean square error MSE is then E expected value of x minus expected value of x whole square is equal to variance of x. So that variance of x will give me the minimum square error. So we can find this variance as by different methods. So we can use first method is just using the theorem that we have seen. I think so it's theorem 3.10. So it says that if we just write sigma x square, so that is summation x belongs to range of x, x minus mu x whole square p x of x. Means if we have this PMF of x and we have this relation for the variance of x, so we have seen that variance of x is E x minus mu x whole square. So we can find just like the expected value of this function. That's the straightforward. The other way is to find variance of x is equal to expected value of x square minus expected value of x square, or which is minus x expected value of x and then square of it. So remember, these are different things. This square is on x square, so this is different, and this is the square of the expected value. So they are not the same values. So we have to be very careful about this. So we can use either of the method to find out the variance of a random variable. Now let's small definition. It's the definition about the moments. Moments of a random variable are simply, we define them as the first one is called as the nth moment, is expected value of expected value of x raised power n. So I will write examples. So just like e expected value of x is the first moment of random variable x, and similarly we can write down the nth central moment is expected value of x minus mu x whole power n. So we see that for n is equal to 2, because the first central moment is 0. If it is 0, we have seen previously, if it is 1, so expected value of the second for n is equal to 2, which is the variance of the random variable x. So that's the second central moment of the random variable x. Now let's look at the example, how we can find out the variance of a random variable. So this is exactly actually the example 3.32, and it says that we have given this PMF of x 1 by 4 for x equal to 0, 1 by 2 for x equal to 1, 1 by 4 for x equal to 2, 0 otherwise. So we will find out the variance by using both methods. So we have previously seen that expected value of this random variable is 1. So we need to find the variance of x. So for finding the variance of x, we can use both the relations. So we are finding with the first method, and it is the summation of x belongs to s of x, x minus mu x whole square into px of x. So this is how we are going to find it, the variance by method 1. So x is actually from 0, 1 and 2 only. So this is 0, 1, 2. We can say that summation x belongs to sx, and s of x is defined here as 0, 1, 2. So for just avoiding this step, so we will write for 0, opening up this summation. So 0 minus 1 whole square into px of x is 1 by 4 plus this is 1 minus e of x is 0, which is mu of x. So 1 square, and this px of x is 1 by 2 plus x is now 2, and this is 1, 2 minus 1 square into 1 by 4. So this is straightforward 1 by 4, this is 0 and plus 1 by 4. So it is 1 by 2. Yeah. So we have this variance as 1 by 2. Now we can use the other method in which we have said that variance of x is equal to the second moment minus the square of the first moment. So we have this first moment, which is the expected value. We can find this second moment, expected value of x square. Again, this is just simple expected value. So the relation is same as x belongs to range of x, x square, px of x. Now we know the range of x is 0 square into 1 by 4 plus 1 square into 1 by 2 plus 2 square into 1 by 4. So this is 0. So this is 1 by 2 plus 1. So this is 1 whole 1 by 2 or 1.5. Now we can find out the variance of x, which is now expected value of square or the second moment minus the square of the first moment. So this is now 1.5 plus 1 square. Sorry, this is minus. I think so I have not made a mistake. Yes, here we have written. So minus 1. So this is 0.5 1 by 2. So we have seen that in both ways we can find out this variance of x exactly the same value, so that we can use anywhere. Now here one more important thing that we must remember by using this variance, that we have seen that x minus mu x square, because of this square it is always greater than or equal to 0. So which implies that variance of x will always be a positive number or greater than or equal to 0. So this is just one important property. And now let's see theorem stating one of the properties of the variance, and it says that variance of ax plus b, which is equal to a square variance of x, and obviously what should be the variance of a constant. As we have seen, the variance of expected value is the variance of the so expected value of the constant value is constant itself. But what would be the variance of a constant value? So variance, actually, if we just look into the definition, variance gives us the spread of the data. So constant cannot have any spread, so that would be 0. So that's why we put it, we will not leave it here, we will just say it is 0. So, and this is a square that comes out here. This is just because of the derivation of this thing. We are not going to prove this thing, but it is still a standard way to look into this thing. So there is another theorem, and that is very interesting theorem, 3.16. Now we have seen in this chapter that there were some families of random variables, and at that point we defined that those families of random variables gives us the freedom to have a single formula, and many different problems that are closely matching to those families can be benefited with the direct formulas, with the direct derivation of those information that we have with us, and we can apply the families all the properties to it directly. Similarly, we can have the we can find out the variances of these things very straightforward. Means just like we have seen the expected value of those families of random variables. So similarly here we could have the variances of those random variables, that we don't have to derive them, we don't have to calculate them, and if we know that this random variable is behaving like certain family of a random variable, so as we can find out the expected value readily, so we can also find out the variance of that random variable easily. Now say if the x is Bernoulli random variable, Bernoulli p, so variance of x will be p into 1 minus p. Similarly, if x is geometric p, so its variance will be 1 minus p divided by p square. Similarly, if x is binomial, np, so variance would be np into 1 minus p. Similarly, if x is Pascal, kp, then variance of x will be k into 1 minus p divided by p square. So if x is Poisson alpha, then its variance is simply alpha. And if x is discrete, uniform, KL, then variance of x is simply L minus k plus 2 divided by 12. So let's look at one more example. Pasted from the book. So it's example quiz 3.8. So it states that in an experiment with 3 customers entering the phone smart store, the observation is n, the number of phones purchased. The PMF of n is Pn of n, which is equal to 4 minus n by 10. N is equal to 0, 1, 2, 3, 0 otherwise. So what we need to find is the expected value of n, the second moment, En square, the variance, and the standard deviation sigma n. So we can find out that from here it's straightforward, or we can create a table to make it more understandable for us. That is Pn of n. For 0, this is 4 by 10, which is 0.4, and for n is equal to 1, it is 3 by 10, which is 0.3, and for 2, it is 4 minus 2 is 2 by 10, which is 0.2, and for 3, it is 0.1. So we can find out the expected value of n, which is now straightforward. So it says that n is equal to 0 to 3 n p n of n. So this would be 0 into 0.4 plus 1 into 0.3 plus 2 into 0.2 plus 3 into 0.1. So that would sum up to be 1. Similarly, the second moment can be found out easily. So second moment would be 0 square 0.4 plus 1 square 0.3 plus 2 square 0.2 plus 3 square 0.1. So which comes out to be 2. Now the variance is straightforward. Variance of n is equal to, we can use this relation of expected value of n's second moment minus square of the first moment. So this is 2 minus 1 square. So the standard so the variance of n is 1. Now the fourth part says that the standard deviation. So standard deviation is sigma n, that is the square root of variance of n. So this is straightforward. Square root of 1 is 1. Now this is somehow the end of this chapter. Not exactly, but they are left with the MATLAB part. So I will suggest that you must go through that part by yourself. That's straightforward. Some of the examples are given, so you can follow those examples to understand how you can produce different classes of or the families of random variables, or you can find out the probabilities of the certain random variables using MATLAB. So that would be great if you would go through these MATLAB examples and understand them if you have. So if you have any problem, you can always discuss with me. So stay blessed. Assalamu alaikum wa rahmatullahi wa barakatuhu.